networks? Yes, many, actually. There are always many ways to solve the same problem, though some ways are better than others. Another mathematical tool we can use is called the Taylor series. This is an infinite sum of a sequence of polynomial functions, x plus x squared plus x cubed plus x to the fourth, up to x to the n. N is the order of the series. Each of these terms are multiplied by their own value, called a coefficient. Each coefficient controls how much that individual term affects the overall function. Given some target function, by choosing the right coefficients, we can approximate that target function around a specific point, in this case 0. The approximation gets better the more terms we add, where an infinite sum of terms is exactly equivalent to the target function. If we know the target function, we can actually derive the exact coefficients using a general formula to calculate each coefficient for each term. But of course, in our particular problem, we don't know the function, we only have a sample of data points, so how do we find the coefficients? Well, do you see anything familiar in this weighted sum of terms? We can put all of the x to the n terms into an inputs vector, and put all of the coefficients into a weights vector, and then take the dot product, a weighted sum. The Taylor series is effectively a single-layer neural network, but one where we compute a bunch of additional inputs, x squared, x cubed, and so on. We'll call these additional inputs Taylor features. We can then learn the coefficients, or weights, with backpropagation. Of course, we can only compute a finite number of these, the partial Taylor series, up to some order, but the higher the order, the better it should do. Let's use this simple Taylor network to learn this function, using 8 orders of the Taylor series. Here's our dataset, and here's the approximation. That's not great. Polynomials are pretty touchy as their values can explode very quickly, so I think backpropagation has a tough time finding the right coefficients. But we can do better. Rather than using a single layer network, let's just give these Taylor features to a full multi-layered network. Let's give it a shot. It's a bit wonky, but this performs much better. This trick of computing additional features to feed to the network is a well-known and commonly used one. Intuitively, it's like giving the network different kinds of mathematical building blocks to build a more diverse, complex function. Let's try this on an image dataset. Well, that's pretty good, it's learning, but it doesn't seem to work any better than just using a good old-fashioned neural network. The Taylor series is made to approximate a function around a single given point, while we want to approximate within a given range of points. A better tool for this is the Fourier series. The Fourier series acts very much like the Taylor series, but is an infinite sum of sines and cosines. Each order, n, of the series is made up of sine nx plus cosine nx. Each sine and cosine is multiplied by its own coefficient, again controlling how much that term affects the overall function. N, these inner multiplier values, control the frequency of each wave function. The higher the frequency, the more hills the curve has. By combining weighted waves of different frequencies, we can approximate a function within the range of 2 pi, 1 full period. Again, if we know the function, we can compute the weights, and even if we don't, we could use something called the discrete Fourier transform, which is really cool, but we're not dealing with it in this video. I hope you see where I'm going with this. Let's just jump ahead and do what we did before. Compute a bunch of terms of the Fourier series and feed them to a multi-layer network as additional inputs, Fourier features. Note that we have twice as many Fourier features as Taylor features since we have a sine and cosine. Let's try it on this dataset. Now, this works pretty well. It's a little wavy, but not too shabby. Note that for this to work, we need to normalize our inputs between negative pi and positive pi, 1 full period. Let's try this on an image. That looks strange at first, almost like static coming into focus, but it works, and it works really well. If we compare it to networks of the same size trained for the same amount of time, we can see the Fourier network learns much better and faster than the network without Fourier features